Hello everybody, welcome back to the channel. Today we're gonna talk about the Laplace transform, which is new chapter for the course. And so today I'm gonna cover three topics. The first, the definition of Laplace transform. Before I do that, I will explain why we need another transform, right? So you may ask, we had phasors, the other things, and why we just need another transform, right? We may have enough. And the second one is I want to take a look at the unit step function and its Laplace transform. And the third one would be the unit impulse function and its transform. So there will be three video clips. Let's jump into the first one. So the first question is, why do we need another transform, right? We did a phasor. Let's look at what we did in the phasor. And in the phasor, we have a linear circuit, but with the linear circuit has to be in steady state and sinusoidal signals. So therefore, you can take the phasor and you can transform the circuit in phasors, and then you can solve the algebraic equations rather than, those algebraic equations would be complex because in J's, impedances, and phasors, right? And you get the responses in phasors, and then you can come back to the time domain by doing the going back to the sinusoidal, right? That's what we did in the phasors, but they only applies to sinusoidal and steady state. What if you have a circuit that's not sinusoidal or not in steady state, and you want to see the transient, right? These things, let's see if you have some disturbance or if you apply some changes in the signal, how that really responds. So that will actually bring the things we're going to talk about today, and we're going to do the Laplace transform. And so this is the Laplace transform, and this could be any linear circuit. So it doesn't have to be in steady state, or it doesn't have to be with the sinusoidal signal. It could be any signal. So once the circuit transform in the S domain, the Laplace domain, and we can do the similar thing, solve the algebraic equations, and get the result. Of course, in this case, would be in S domain, not in phasors. But then we do the inverse Laplace transform, come back to the time domain. So that's what we will do in these two chapters to cover these concepts. So this is called the inverse Laplace transform. Okay, I hope you're convinced that this is going to be really useful, not only in circuit but also in the controls. The Laplace transform, that's really very foundation for the control. Either you do the classical control or you do the modern kind of the matrix-based, the state-based controls. And the Laplace transform is really foundation to all the control courses. When you learn 13 in MSU, you will learn that very quickly. And let's look at what's the definition of the Laplace transform. First, the Laplace transform of T, this is denoted by the Laplace transform of Ft, and this is going to be the definition of this is going to be if you integrate this from 0 to infinity, and Ft e2 minus st dt. And normally you can integrate from 0, but to be sure you start with 0 minus. The 0 minus is necessary when Ft has an infinite step change at t equal to 0. Right? So otherwise you can just the same using 0, or we will see as we do the examples. So this is the definition, and since you integrate over time, the time t will disappear. It's going to be a function of s. So we denote that use a capital F the uppercase F and a function of S. So this is Fs is the Laplace transform, is the Laplace transform of Ft, and S here, S is a complex variable. S is a complex variable, and S typically equal sigma plus j omega. That's the so the sigma is real and omega is real. Okay, so this is the definition. So it sounds like mathematical, right? But this definition is really useful in very practical sense. Not only allows us to do the control, to analyze the circuit without solving the differential equation in this course or in other course doing controls, but it really gives you the insight to the what's going on in the circuit. So that's really important, right? I hope you really get the idea of not just a mathematical transform. This is really used not only in the academic world but also in industry. And you do you transform, you model the things in the S domain, and you do the body plots. Later we'll see this. And so this is really very useful tool, very foundational to a lot of things we do in engineering in general. Okay, so this is a short video clip of introducing the concept of Laplace transform and why we need it. And I will start another video clip to just do a Laplace transform on the unit step function. See you in a moment.